Hi guys, I want to show you another example problem. This time we're looking at projectile motion and we're thinking about both the horizontal direction and the vertical because our cannonball is actually going to be launched this time, not just dropped. So let's look at the problem. A cannonball is launched horizontally off of a 50-meter cliff with a velocity of 20 meters per second. How far from the edge of the cliff will it land? So let's draw a little sketch. We've got our cannonball. It's being launched horizontally. And it's going to land some distance delta x away. All right. So we want to know how far it's going to land. Well, let's write what we know. We know that velocity initial in the y direction is 0 because it's just launched straight horizontally. So that means there's no vertical motion initially. We know that velocity initial in the x direction is 20 meters per second. We know that delta y is 50 meters, and just like the previous problem, I'm going to say that this is going to be y equals 0, and I'm also going to say that downward is the positive direction and to the right is the positive direction. So that way I can say that acceleration in the y direction is a positive 9.81 meters per second squared, or g. And that way I can not have any imaginary numbers. Yay! We also know that acceleration in the x direction is 0. There is no acceleration in the x direction. It's going to move with the same velocity in the x direction the entire time. So if I draw a motion map in the horizontal, it would look something like this, right? Constant velocity. And if I was going to draw a motion map in the vertical direction, it would look something like this, right? So that way, I can show that it's accelerating in the y direction and not in the x direction. Cool. What we don't know is time. We don't know delta x. The reason it's important for us to know what time is because our equation that we will need to use, delta x equals v naught t plus 1/2 at squared, it has time in it. We can't avoid that, right? So remember thinking in the x direction. Let's plug in a 0 first just so we don't freak out. We know that acceleration in the x direction is 0, so let's cross that out. So we're left with delta x equals v naught in the x direction times time. We still need to know what time is. So let's find time first, right? We're actually going to use the same process as in the previous video. We know that delta y equals v naught yt plus 1/2 at squared. We know that the initial velocity in the y direction is 0, so we get rid of that. We know that acceleration is g, so we just say delta y equals 1/2 g t squared, just like last time. I'm looking for t by itself, same process as before, so I'm going to do it fast. 2 delta y divided by g, square root of that is t. If I plug in values, the same values as the previous problem, so it's going to end up being 2 times 50 divided by 9.81, which is still that 3.19 seconds. So even though we launched the ball this time, or launched the cannonball this time horizontally, the time it takes to the ground is the same, because it turns out the only thing that matters for determining the time of a projectile on Earth is that height, that 50 meters. That is what is most important, okay? Height is what determines your time to the ground. Okay, now we know what time is. Let's plug it in. So delta x equals v naught. So v naught in the x direction, that is 20. And then time, that is our 3.19 seconds. So if I multiply that together, I'm going to get 63.8 meters. So that means we have changed our horizontal position by 63.8 meters. Not bad. Hope this has been helpful.